This conference will now be recorded.
Students. So up to the last session, we have discussed about the first chapter of your probability theory and stochastic process subject. Now we are entering into the second chapter. So here, first let us see the contents of the second chapter. So here in the second chapter, so first in the very first chapter, we have discussed about probability and random variables. So in the random variables, we have discussed about the definition of the random variable and how to define the random variable in fact, and what are the different types of random variables, and what are the conditions for the function to be a random variable, and also the distribution function and density function of the random variables are discussed. Now we are moving to operations on the random variable. So here, as we have discussed only about a single random variable in the first chapter, the extension to that is operations on single random variable, right? So in the operations on the single random variable, we are going to see expected value of random variable and also the expected value of function of a random variable and the moments about the origin. So we are going to see what is moment, and also we are going to see what is moments about the origin and also the central moments. In fact, the central moments are nothing but the moments about the mean value, right? So here we are going to see along with the moments variance and skew. So these are mean, variance, skew. These are nothing but the statistical parameters of any experiment. So here, as I said in the very first chapter, every experiment is a random experiment, and in the real time, after conduction of the experiment, we are going to define or represent that particular experiment by using a random variable. And after defining the random variable, we are going to define the distribution and density function for the analysis of the particular experiment, right? So here, to analyze that particular probabilistic model, we need the statistical analysis, and for the statistical analysis we take the help of the statistical parameters, and those statistical parameters are nothing but mean, variance, skew, and in fact we have more number of statistical parameters, and we can derive by using the moments of the random variable, right? And at the same time we are going to see Chebyshev's inequality, and we do have Markov's inequality, and characteristic function and moment generating function. As I said, the moments are going to give the statistical parameters for the statistical analysis of the experiment, and here we are going to use characteristic function and moment generating function for generating the moments, right? And we are going to see what is characteristic function and what is moment generating function and what are their uses and properties. And also we are going to discuss about transformation of a random variable, and in some scenario here, uh, for example, for any real-time experiment, that particular experiment is defined by using one particular random variable, but here I would like to analyze that particular experiment by using or by representing another random variable. I would like to transform the random variable which is already defined into my convenient way, that is a new random variable, and there I need to apply the transformation. And in the transformation we are going to see different types of transformation like monotonic and non-monotonic, and here the random variable defined may be a continuous or maybe a discrete, and we are going to see monotonic and non-monotonic transformations for continuous and discrete random variables, right? And this is all about operations on single random variable. And next we are going to enter into multiple random variables. Why? Because if you consider any real-time experiment, and single random variable may not be sufficient to define that probabilistic model, and sometimes we may need to define more number of random variables, or we may need to represent any experiment with the help of more number of random variables. And therefore we are going to see how to define the multiple random variables for any experiment, and we call it as vector random variables, right? So we are going to see what is vector random variable and how do you write same as your single random variable, and whenever the random variable is defined for any experiment, and we need to take the distribution and density functions for the representation of the probabilities in the experiment. Similarly here, even in the multiple random variable case also, we take the distribution density functions, but as we have multiple random variables here, we call it as joint distribution and density. And we are going to see joint distribution and density and also its properties. And we are going to see even marginal distribution and density functions. And along with that, we are going to see conditional distribution and density. In the very first chapter, we have discussed about the conditional distribution and density, and there I have mentioned that there are two methods to apply conditioning, and method one is discussed in the first chapter, and where the conditioning is applied by the event, where the event is selected by using the same random variable. If at all, if the event, I mean the random variable is conditioned by an event which is defined by using the other random variable, that comes under method 2, and that part we are going to see in this particular chapter, that is conditional distribution and density. And here we are going to take even same as in the first chapter, we are going to take point conditioning and interval conditioning, and also we are going to see what is statistical independence and what is the condition for any two random variables to be statistically independent. And if at all, if any two random variables are considered or more number of random variables are considered for any experiment, we are going to see the sum of random variables and also the distribution and density functions of sum of random variables, and that part also we are going to discuss here. And central limit theorem. In fact, in the first chapter we have discussed about Gaussian distribution, and also we have considered several experiments, and we have taken the outcomes of the experiments by taking various trials, right? So if at all, if the number of trials are increased, and if at all, if the number of trials leads to infinity, and irrespective of the type of the experiment, the distribution function or the density function leads to Gaussian, and that will be given in the central limit theorem. And we are going to see what is central limit theorem in this chapter, and also we are going to see unequal and equal distributions in this particular chapter, right? So in the very first part of the second chapter, we are going to discuss about operations on the single random variable, and then we are going to introduce multiple random variables, and in the multiple random variables we are going to see the distribution functions, density functions, and so on. And after taking the multiple random variables, same as for single random variable, we are going to see operations on multiple random variables. So in operations on multiple random variables, again, so same as your single random variable, the only one operation that you can apply is expectation. So therefore, we are going to say what is expectation of this particular multiple random variable case. That is, if any experiment is defined with more number of random variables or multiple random variables, by taking a function of such random variables, we are going to find the expectation, and that is nothing but operation on that particular function, and which can give the statistical parameters of the random variables, right? And therefore, for finding the statistical characteristics or statistical parameters, we consider the joint moments about the origin and about the mean. And in other words, we can call it as joint central moments, right? And also we are going to see what is joint characteristic function, which can generate the moments, which leads to the statistical analysis. Am I clear? Right? And also we are going to see what is jointly Gaussian random variable, and there we are going to take two random variable case and n random variable case, and also the properties of jointly Gaussian random variable. Same as on the single random variable, we do apply the transformations on multiple random variables, right? So this part we are going to discuss. So the advantage of the second chapter is, if you are familiar with the first part, in the sense operations on the single random variable, you can easily understand and you can easily remember the operations on the multiple random variables. That is the last part of the second chapter, right? So let us move on to the first part, that is operations on single random variable, right? So why do I need to take the operations, right? So here, as I said, the only one operation. First of all, what is operation actually here? So you might have seen in the functions, or you might have seen in the signals. So for the signals, if you consider, the operations may be arithmetic operations, right? In the sense, arithmetic operations, in the sense we can add any two signals, or we can multiply any factor to the signal amplitude, or we can shift the signal to either left or right. So why do we take all such operations? Ultimately, to analyze the signals. Similarly, here we are going to take some operations on the random variable. So why do I need to apply the operations? Actually, that particular random variable is defined for the probabilistic model. By applying the operations on the random variable, I am going to take out the statistical parameters of the experiment, right? So therefore, I'm going to take the operations on the single random variable. The only one operation that I can apply on the random variable is expectation, right? Expectation. Just let us take one example, and there you can understand why do we need to take the expectation. For example, I have one application. What is the application? 90 people are randomly selected, and the fractional dollar value of coins in their pockets is counted. So 90 people are randomly selected. Let us take in US, in the United States of America, 90 people are randomly selected. And after selecting, I'm just counting the fractional dollar value of coins in their pockets. Usually, we keep some notes as well as some coins in the pocket. So by taking the coins count, I'm going to take the fractional value of the coins in their pockets, right? And if the count goes above a dollar, the dollar value is discarded. So my intention is only to take the fractional value. So if it is above the dollar, for example, I have $1.2 in my pocket, I'm going to discard that one. I consider it as 0.2, right? And only the portion from 0, what is that symbol? Stands for pennies or cents. 0 cents to 99 cents. So like in India, we have the representation of money, I mean, as rupees or pies, and in the United States of America, and we take it as dollars and cents, right? So $1 equal to 100 cents, right? So therefore, dollar value is discarded, and only the portion from 0 cents to 99 cents accepted. It is found that 8, 12, 28, 22, 15 and 5, altogether 100. People had 18 cents, 45 cents, 64 cents, 72 cents, 77 cents and 95 cents in their pockets respectively. Right? 8 people are having 18 cents, 12 people are having 45 cents and 28 people are having 64 cents and so on. Then find the average of these values. Average of these values. So you are supposed to find the average. Usually, how do you take the average? How do you take the average? Generally, if I have 10 numbers, generally what I'm going to take average in the sense sum of all the values or all the numbers by total number. That is the general phenomena we have whenever we are taking the average. But in this case, it is not the deterministic experiment, it is a random experiment. So you cannot take the average as the sum of all the values, right? So why? Because when I say 8 people, so which 8 people are having 18 cents? Which 12 people are having 45 cents? We do not know, right? So therefore, in this case, that is how to find the average, right? That is the question we have whenever we have a random experiment. That random experiment is selecting 90 people randomly and counting the fraction of dollar values in their pockets, right? How to find the average? So we have the solution. The solution is nothing but expectation. Expectation, right? So what is expectation? What is expectation? Expectation is the process of averaging when a random variable is involved. That is generally averaging we know, but here process of averaging when the random variable is involved is expectation, right? For a random variable x, we denote the expectation as e of x, or the process of averaging as e of x, right? And we can also call the expectation as the mathematical expectation of x, or the expected value of x, or the mean value of x, or the statistical average of x, right? So any way you can call mathematical expectation or expected value or mean value or statistical average, right? So as I said, it is a statistical property or statistical parameter of a random variable, right? And the usual notation of the expectation is x bar, which is equal to e of x, right? So what is expectation? It is the process of averaging, right? So here in general, the expected value of the random variable, continuous random variable x, is defined by, how do you represent? E of x equal to x bar equal to integral minus infinity to plus infinity small x into fx of x dx, right? So generally for finding the average, we count, we take the sum of all the numbers by total number we used to take. But when the random variable is involved, ultimately the density function will come into the picture, right? So therefore the expectation is integral minus infinity to plus infinity small x into fx of x dx whenever the random variable is continuous, right? So if at all, if the random variable is discrete, so here the density function can be taken in the form of probability values. So therefore we can take the expectation as x bar equal to summation I equal to 1 to n xi into p of xi, right? So where p of xi is the probability values of xi respectively when I equal to 1 to n. That is the way to find the expectation. So now let us move on to the previous problem, the same problem. Now let us check how to solve the problem, right? So how to take the solution now? So what is the sample space now? 90 people. But what is the random variable? The random variable is 18, 45, 64, 72, 77, 95. The sense what? 18 cents, 45 cents, 64 cents, 72 cents, 77 cents, 95 cents. That is the fractional value of the dollar is nothing but random variable. I need to find out the average value of these fractional dollar values, right? So therefore I'm taking first the probabilities. So here, what are the probabilities given? What is the given data? So 8 people are having 18 cents. 12 people are having 45 cents. So whenever I pick a particular person, what is the probability that that particular person is having 18 cents in his pocket? 18 cents in his pocket. Whenever I pick any particular person, what is the probability that particular person is having 18 cents in his pocket? Ultimately 8 by 90. Why? Because out of 90, 8 people are having 18 cents. Similarly, 12 people are having 45 cents. So therefore, the probability of occurrence of xi means what? Xi means the elements of the random variable. When I equal to 2 here, x2, it is x2. The probability of getting 45 cents is 12 by 90. If I know the elements values of the random variable and the respective probabilities, I know how to find the average. So that is average is expectation of x equal to x bar equal to summation 1 equal to I equal to 1 to n xi p of xi, right? By substituting the values, xi is x1 is that value. What is that value? 18. But I am saying here in dollars. So therefore, it has become $0.18 into 8 by 90 plus 0.45 into 12 by 90. So like that, you can take the sum and the resultant value is $0.632, right? So this is the way to use the expectation, and whenever you need to find the average of the random experiment or statistical average value, right? So now what is the next one? Expected value of a function of a random variable. And sometimes the random variable is defined and in the form of a function. That is, if a function is considered, that is where the function is function of a random variable, we can also find out the expectation of that particular function. Expectation of that particular function. So here in the let x of x is a real function of ex, then its expected value is given by e of g of x equal to expectation of g of x. In the previous case, we have taken expectation of x equal to integral minus infinity to plus infinity small x into fx of x dx. But in this case, g of x into fx of x dx when x is continuous. If at all if x is discrete, we take the summation, but in the place of small xi, we take g of xi, right? So that is the difference between the expectation value or expectation value of random variable and the function of random variable, right? Am I clear? And n may be infinite for some random variables. There is no limit that only these many elements must be there, and there may be infinite number of elements for the random variable, right? Now the next one is conditional expectation or conditional expected value or conditional mean value. Whenever you are supposed to find the mean of any random variable or statistical average of any random variable, but that particular random variable is conditioned by any other event, so we have discussed what is conditional distribution and conditional density in the first chapter, right? So when the condition will come into the picture, if at all, if any one particular random variable is conditioned by another event, right? We have taken one example there, one simple application we have taken, one problem, that is drawing a card, so that is whether the card drawn is king or queen or jack. First experiment. Second experiment is without replacing the card, what is the probability that the drawn card is either jack or king or queen? So here the condition is what? The card is not replaced. Card is not replaced. So like that, we can apply the conditioning to the experiment. Or if I apply that conditioning, how do you find the expectation value or statistical average? So here the conditional expected value of x is denoted by e of x given b, right? So that you need to read as x given b. It is given by e of x given b equal to, earlier we have taken the density function of x as fx of x, but now you need to take conditional density function. What is that fx of x given b? Conditional density function of the random variable x, right? You know what is conditional density function of the random variable? Already we have studied in the first chapter. Am I right? So therefore, if the event b is defined as x less than or equal to b, where b is in between minus infinity to plus infinity, I can substitute that. I can write the density function as we have discussed in the first chapter. We can write the definition as fx of x given b or x given x less than or equal to b is fx of x by integral minus infinity to b fx of x when x is less than b and is 0 when x is greater than or equal to b. So this is the conditional density function of the random variable x, which is already derived in the first chapter. If I substitute the same function value in the above integration, how can I write the resultant conditional expectation? Conditional expected or conditional expectation of x given b is equal to, here when I substitute this, so what I'm going to take here, as it is existing only for minus infinity to b, the limits will be from minus infinity to b. All right. So here fx of x given b is equal to fx of x I am taking. So therefore x into fx of x, and in the numerator anyway it is constant with respect to x. So therefore integral minus infinity to b fx of x dx. Right. So here therefore the resultant can be written as integral minus infinity to b x into fx of x dx by integral minus infinity to b fx of x dx. That is conditional expectation. Am I clear about conditional expectation? So we have discussed what is expectation of the random variable, what is expectation of the function of the random variable, and what is conditional expectation when the random variable is conditioned by any other event, right? So which is the mean value of the x when x is constrained to the set x less than or equal to b. Am I clear? There is a constraint on x, right? Now, properties of expectation. What are the properties we have for the expectation? If c is a constant, for the constant value, the average is equal to, again the same, e of c is equal to c. When c equal to 10, expectation of 10 is 10 only. Can I get any other value for the average of the constant? Average of 10 is 10 only. Average of 100 is 100 only, right? Or if g is a function and for any random variable x, if at all if I have the function as g of x, where x is the random variable, and if it is multiplied by any constant, then I can write the expectation as c into e of x or e of gx, right? Next, let g and h are g and h be functions, and let a and b are constants. G and h are functions and A and B are constant. For any random variable x that may be discrete or continuous, how can I write E of A into G of x plus B into H of x equal to A into expectation of G of x plus B into expectation of H of x, that is linearity property. Expectation also obeys linearity property, right? And the third property is if x and y are any random variables that may be discrete or continuous or dependent or independent, I can write the expectation of their sum equal to sum of individual expectations, right? Sum of individual expectation. And also, if at all if the random variables to any two random variables are independent, then I can also write E of xy equal to E of x into E of y. So these are very, very important properties while applying the expectations, right? So E of g of x into h of y is E of g of x into E of h of y, right? So let us take a simple problem here. The probability distribution of x is given as shown in the table below. Then find E of x and E of x square. So what is the given data here? The elements of the random variable and the respective probability values are given. That is, when x equal to 0, probability is 0.16. When x equal to 1, probability is 0.48. When x equal to 2, probability is 0.36. Am I clear? So what are you supposed to find? Expectation of x and expectation of x square. The first one is using the direct formula. Second one is you have to use expectation of the function of the random variable, right? So you know how to apply the formula. What is the formula? E of x equal to summation xi into p of xi. So let us see the solution. So here we are given the data, probability values for the elements x equal to 0, 1, 2. We know the formula E of x or mean value equal to summation for all x into p of x. So what is x? 0. So therefore 0 into 0.16, 1 into 0.48, 2 into 0.36. So here that is nothing but expectation of x. So what is the answer? 1.2, right? So that is the mean value or expectation of x, right? So here you need to see that the elements, all the elements must be considered, right? 0, 1, 2, all the elements must be considered, and to find the mean value. And the next one is E of x square. We can also call it as mean square value of the random variable. E of x square equal to, and in the place of x I am writing x square. So therefore 0 square, 1 square, 2 square must be taken instead of 0, 1, 2. Therefore the resultant will be equal to 1.92. That is the way to find the expectation of x and x square, right? Let us take another problem. Let x be a random variable defined by the density function. What is the density function given? Fx of x equal to 5 by 4 into 1 minus x power 4 in the interval 0 less than x less than or equal to 1 and equal to 0 elsewhere. Find E of x. Whether the random variable is continuous or discrete in this case? Yes, it is continuous. Why? Because the limits for the elements of the random variable is given as 0 less than x less than or equal to 1. So therefore it is nothing but continuous random variable. And also the density function is not given as series of impulses. Ultimately, for the discrete random variables, the density function is series of impulses, but it is not given as series of impulses. It is given as just a function. Therefore, directly you can consider that the random variable is continuous random variable, right? So how to find out the expectation? We know the formula. What is the formula? e of x equal to integral minus infinity to plus infinity small x into fx of x dx, right? Can I apply the formula? Yes, let us see. Since x is a continuous random variable, e of x equal to integral minus infinity to plus infinity x into fx of x dx. Fx of x is given as 5 by 4 into 1 minus x power 4 dx. By substituting that, I am just finding the integration with the basic mathematics knowledge, and the resultant is 0.417. This is the way to find the expectation of continuous random variable, right? Next one is, let us take another problem. Find the expected value of discrete random variable x, whose probability distribution is given below. Here, the probability values are given, same as your previous problem, before the previous problem, that is discrete random variable case. Am I right? So elements are given as 1, 2, 3, 4, 5, and the respective probabilities are given as 0.1, 0.1, 0.3, 0.3, and 0.2. Right? Just pause the video and try to solve. As we have done already a problem based on the same formula, just try to solve. Yes. Let us come to the solution. As the x is a discrete random variable, we know the formula. Summation I equal to 1 to n xi into p of xi. E of x is summation. Right? Substitute directly. 1 into 0.1 plus 2 into 0.1 plus 3 into 0.3 plus 4 into 0.3 plus 5 into 0.2, which is equal to 3.4. Right? So easy problem. Can you do it? Yes. The next one is moments. And the next topic is moments. What is moment actually? Moments define some statistical values of the random variable, as I said, and we need to find the statistical values. So here, moments define some statistical values of a random variable which are useful for the statistical analysis of any experiment, right? Right. So moments play an important role in the theory of probability and applications problems. Theory of probability and application problem. So why? Because usually two types of moments are defined for a random variable. So what are the two types? One is moments about the origin, other one is moments about the mean value. So already we have seen what is mean, nothing but expectation of random variable or x bar or e of x. One is moments about the origin and the other one is moments about the mean. So let us take what is moments about the origin, right? First one, moments about the origin. Moments about the origin of a random variable are denoted by small m, right? So here the suffix of small m, like m1, m2, m3, and so on, indicates the number of moment of the random variable. Like m1 is first moment, m2 is second moment, and so on, right? And the nth moment about the origin of the random variable x is given by the general term is m suffix n equal to expectation of x power n. So what is the moment of the random variable about the origin? Expectation of x power n, right? So that is integral minus infinity to plus infinity x power n into fx of x dx when x is continuous, right? So similarly, if the random variable is discrete, m suffix n equal to expectation of x power n or summation I equal to 1 to infinity small x power n into p of xi when x is discrete, right? Simple formula. Moments about the origin. Here, when n equal to 0, what it is, that is when equal to 0, m0 equal to what? E of our expectation of x power 0, e of x power 0 in the sense e of 1, As per the property of the expectation of constant is again the same constant, therefore 1. So the 0th moment about the origin is ultimately 1. And next, if n equal to 1, the first moment about the origin will give what? The mean value of the random variable. M1 equal to E of x1 or E of x, which is nothing but x bar, right? The first moment about the origin will give the statistical average or mean value, right? If n equal to 2, the second moment about the origin, that is m2 equal to E of x square, that is nothing but x square bar, so which can also be called as the mean square value of the random variable x. So that is the moments are giving the statistical value, maybe statistical mean or mean square value, right? Next, moments about the mean are central moments. Moments about the mean of the random variable are also called as central moments. So here, moments about the mean of a random variable are denoted by mu. About the origin are denoted by m. About the mean are denoted by mu, right? So the number of moment of the random variable is indicated with its suffix, same as your moments about the origin. M suffix n is nth moment. Similarly, mu suffix n is nth moment about the mean or nth central moment, right? So the nth moment about the, sorry, it is not origin, it is mean of the random variable is given by what? Mu suffix n equal to expectation of x minus x bar whole power n equal to integral minus infinity to plus infinity small x minus m1. M1 is first moment about the origin or the mean value or expectation of x or x bar, right? X minus m1 whole power n into fx of x dx when x is continuous, or when x is discrete, we know how to write the expectation of x minus x bar whole power n, which is equal to summation I equal to 1 to infinity x minus m1 whole power n into p of xi, right? So this is about the central moments or moments about the mean. Here we have some statistical parameters, and the statistical parameters are variance and skew. So we can find the statistical parameters like variance and skew by using moments, right? So here, how do you find? If n equal to 0 in the previous case, that is the 0th central moment is what? E of x minus x bar power 0 or 1. Similar way, for 0th moment about the origin is also 1. If n equal to 1, the first central moment is equal to what? 0. Whereas the first moment about the origin is mean value, statistical mean value, right? If n equal to 2, what is this? Second central moment is E of x minus x bar whole square. If I expand that x minus x bar whole square, I can write it as E of x square minus 2x x bar minus x bar square, right? So here I am taking the expectation into the equation. How can I write E of x square minus, what is x bar actually? Mean value. So mean value is always constant and independent of x. Just do remember this. That is x bar is constant. So as it is constant, it is coming out of the expectation. Therefore 2 into E of x into x bar, right? So therefore, how can I rewrite the equation now? M2 minus 2 into M1 into M1 plus M1 square, which is equal to M2 minus M1 square, right? So that is second central moment equal to m2 minus m1 square. This is the relation between central moments and moments about the origin. And here mu2 equal to m2 minus m1 square. And here the note is the second order central moment mu2 is also called as variance of the random variable. So usually here the variance, I mean the non-negative square root of the variance is called standard deviation, and it is denoted by sigma x. The variance is denoted by sigma x square. Standard deviation is denoted by sigma x. Standard deviation or variance are used to measure. In fact, it is a measure of the dispersion of the density function of the random variable about the or from the mean value. That is, when I have the mean value, when I have the distribution function, when I have a distribution function, so ultimately here the distribution function will get dispersed or will get away from the mean value, how much amount it is dispersed, and that is the dispersion of the particular distribution from the mean value can be known by finding the variance or standard deviation. So therefore, the application or the variance or standard deviation is what? It is the measure of dispersion, right? So we can write therefore sigma x equal to under root mu2 equal to under root m2 minus m1 square, right? So if n equal to 3, the third central moment e of x minus x bar whole cube, if I expand the equation e of x cube minus 3x x bar into x minus x bar minus x bar cube. So similar way, if I take the expectation into the equation, how can I write mu3 equal to m3 minus 3 m1 m2 minus 2 m1 cube. So the third order central moment is also called as skew of the density function. It is another statistical parameter like variance and standard deviation. So total we have discussed. Statistical mean is one statistical parameter. Mean square value is another statistical parameter. Variance is another statistical parameter. Standard deviation is another statistical parameter. And the new one is the skew value. So what is the application of skew value? Variance and standard deviation are for to measure the dispersion. Measure of dispersion. The skew value is the measure of asymmetry, that is whether the distribution function is symmetric or not. The measure of asymmetry of density function about the mean value. The normalized third central moment is another parameter. We call that parameter as coefficient of skewness. Coefficient of skewness. So let us take a simple problem here. So find, let x be a random variable with PDF. PDF stands for probability density function given by fx of x equal to cx square when mod x is less than or equal to 1 and equal to 0 otherwise. What do you mean by mod x less than or equal to 1? What do you mean by mod x less than or equal to 1? The condition is x less than or equal to 1 and x less than or equal to 1 and x greater than or equal to minus 1. In the sense, the limits for x are in between minus 1 and plus 1, right? So only the function exists in the interval minus 1 to plus 1 and is 0 otherwise. Then what are you supposed to find? Find the constant c and also find the expectation of x and the variance of x and also find the probability of x greater than or equal to 12. So here if you observe, it is a mixture of first chapter and second chapter. The knowledge of first chapter you need to have and second chapter also you need to have. Why? Because how do you find the constant c? Just pause the video and try. Yeah, coming to the solution, we all know that the property of density function is the total area under the density curve is equal to 1, right? So therefore, I'm just taking the same equation, integral minus infinity to plus infinity, fx of temporary variable u du equal to 1, right? So anyway, the density function is existing only in the interval minus 1 to 1. Therefore, integral minus 1 to 1 c into u square du equal to 1, right? So if I solve the equation, I can get the constant value as 3 by 2. So therefore, how can I write the density function now? Fx of x equal to c is 3 by 2. Therefore, 3 by 2 x square in the interval minus 1 less than or equal to x less than or equal to 1, right? So now coming to the second one, how do you find the expectation? We know the formula. E of x equal to integral x into f of x dx, fx of x dx. The same formula is applied here. We know the limits from -1 to +1, right? So what is the variance? Variance is nothing but second central moment, or mu2 or sigma x square equal to, already we have derived, what is the formula? So this, what is the formula? M2 minus M1 square. M2 is nothing but E of x square. M1 is E of x. So therefore, if I use the same formula, so what is the answer I'm going to get? E of x square minus E of x whole square. Directly I'm substituting, I'm getting the answer 3 by 5. So this is the way to solve the problem, right? Similarly, third one is what? Probability of x greater than or equal to 1 by 2. How do you write, how to write the value? Simple property you need to use, property of density function. By using the property of density function, how do you calculate? From x greater than or equal to 1 by 2. Therefore, 1 by 2 to upper limit is 1. Therefore, 3 by 2 into 1 by 2 to 1 x square dx. 7 by 16 is the answer. This is the way to solve. Let us take one more problem. Already we have done the same problem, but there we have calculated E of x and E of x square. Same values are taken. The probability distribution of x is given as shown in the table below. Then find the variance, right? See once, E of x minus x bar whole square is nothing but summation, since it is discrete, x minus x bar whole square p of x. Direct substitution, right? 0 minus 1.2. Why? Because already we have derived the E of x earlier. Mean value is known. 1 by 2 is the mean value, right? 1 minus 1 by 2 whole square. Similarly, 2 minus 1 by 2 whole square into 0.36. The resultant is, you can get the answer as 0.48. And we have another method also. What is the other method? Using the relation between central moment and moment about the origin. So what is the relation? Just think once. So this is the way to find variance and standard deviation, right? So here, what is the formula? E of x square minus E of x whole square. We have derived E of x square. We have calculated E of x. So therefore, we can just verify whether it is correct answer or not, right? E of x square is 1.92. Already got. E of x is 1.2. So 0.48 is the calculated one earlier. You can check the answer, right? So this is the way to solve the problems related to expectation. Am I clear? Thank you. We'll continue in the next class.